Okay, so the discussion this week has to do with inferential statistics. And as the name implies, inferential means you are making a general statement on the basis of some particular instances. So if we assume the larger population, typically when we do research, we collect a sample from the larger population and do something to that sample. Let's say we are testing a new drug or finding a better way to get students to study some material. We will do that work with that sample. And based on what we find from that sample, we will then be able to make an inference to the larger population on the basis of what we have found for the sample. That is the essence of inferential statistics. And that is the bedrock idea underlying everything that we do in research in this discipline of psychology. Everything involves the drawing of inferences from a particular sample to that of a population. Let us see just what a representation of this idea is. So, if we imagine that this is the entire population, let's assume the population of US college students. Now, obviously, nobody can tell you at any specific time the number of US students that are there. We do not know that. So, as we say, it's a population of unknown size. But let's assume I am doing a study looking at how students can best perform on college algebra test. If you are a college student, you are more than likely to take a course in college algebra, regardless of the discipline that you are going into. So I want to have a better way of getting students to perform well on this college algebra test. I have found a way of doing that. Now, because I cannot do my study or experiment on the entire population of US college students, I am going to do the study on a sample which I'm drawing from this entire body of college students. Now, before I had done the study, if we assume that you go from place to place collecting sample sizes of 10 each, that is, we draw 10 students each and we give them this college algebra made up of, say, 100 questions. We're going to get a variety of performance based on the math abilities of these individuals who are drawn in all these samples. So let's take a sample size of, say, 10. So if we say 10 and we have this, we draw a sample size of 10 students and we give them just a random college algebra test made up of 100 questions. If we consider this sample 1, maybe the first student gets 2 out of the 100 questions. The second student gets 10, the third 15, all the way until the 10th student who gets 30. So that is for this sample of 10 students that have been drawn from the unknown size of college students in the US. We are drawing 10 at each time. So for these 10 students, we know their individual scores. And so we can find the mean score for that sample. So if the first student got 2, the second 10, all the way to the 10th student getting 30, we will add up all their scores, and this gives us 169. that is the sum of the scores, is 169. To find the average, or the statistical term mean, we sum up all the scores and divide by the number of observations. The sum is 169, number of observations is 10. So 169 divided by 10 gives us 16.9. So that is the average score for this sample of students on that 100 algebra question test. Then we get another sample of 10 students, and this is their performance. They were not that good, but we get nevertheless the average score, which is the sample mean for sample 2, is 5.4. We can continue to do that for the number of possible samples that we can get from the population of US students. And that will be 10 at each time. We can find the sample mean every time until we exhaust whatever number we get. Now, this sample has specific numbers, so we can actually draw a graph of the frequency of these numbers for sample 1. So if we imagine that we want to draw the frequency distribution, come up with a frequency distribution for this sample 1, it will look something like this. So this is the scores that we got for that sample 1. And the scores that we got are listed under this column here. One person got 2, another person got 2, then there was 10, 12, 15, 18, 20, and 30, the last one being 45. Now, if we look at the frequency, that is how many 2s were in that sample of 10, there were 2 people who got 2. One person got 1, one person got 12, 2 people got 15, one person got 18, 20, one person got 1, 30, there was 1 person, and 45, 1 person. So the frequency that we have here corresponds to the number of individuals who were in that first sample, that is sample 1. So if we go back briefly to look at that, we can do this and see that the first sample had 10 students, and this is the column of scores that we got. There were 2 people who had 2, the first one and the 8th one. They both got 2. Then if we consider the number, I think number 15, yes, we got 2. There was the 9th person got 15, and the 3rd person got 15. So this is what we have plotted over there in terms of we have looked at the scores and the frequency. That gave us the frequency distribution. So let's go back quickly and look at that. This is the score. The scores are here and the frequency. So for this sample, we have now a frequency distribution table, which we can translate into a frequency graph, which technically is called a frequency polygon because it plots the midpoints, but we will come to that later on. But if we plot the frequencies on this graph, the number 2, there were 2 people who got that. And then the number 12, 1 person got that. The number 15, 2 people got that. The rest, 1, 1, 1, and 1 for all these numbers. So this is what a frequency graph or frequency polygon will look like for sample 1. Now we can do the same thing for sample 2. We can do the same thing for sample 3, and so on and so forth. This is for each sample. But how about the entire population? Mathematicians and statisticians have said, yes, we can do similar thing That is, we can plot a frequency graph or frequency polygon for the entire population in terms of the samples that we think we can collect from the entire population. So if we assume these students whose exact population we don't know are being sampled 10 at each time, and we are plotting the sample means against the frequency, we can get a frequency distribution that applies to the entire population of students. Now remember, we don't know the actual size of the students, and therefore we don't know the actual number of samples that we can draw from the population of students. But mathematicians and statisticians have come up with a way that can allow them to mathematically derive what it will look like were one able to collect all the possible samples that one can get for this population of US college students. And if we go to the next graph, this gives us the same idea. So we assume that the sample mean for this sample was 10, the sample mean was 5, 8, and so on, and we can draw a whole number. But mathematicians say that if we were to do that for the entire population and we plotted their scores against the frequency here, we wrote frequency here, and we had the scores here, and we plotted the sample means. Remember, it's the mean scores for each of the samples that we would draw from the population of college students, and we plotted that. This, according to mathematicians, is the nature of the distribution that we will get. Majority of the scores will be in this portion of the graph, whereas a few will be at the very bottom and at the very top. That is, low scores will have just a few scores, and very high scores will have just a few scores in terms of frequency, but the majority of the scores would be here in the middle. This is the idea behind all inferential statistics that we do in psychology and other social sciences, criminal justice, sociology, etc. So, again, this is the nature of the distribution that we will get were we fortunate enough to be able to sample equal sizes from the population and plot their mean scores against the frequency. We will get this kind of a graph, and this is called the normal distribution curve or graph. The usual popular term that we refer this to is the bell curve. So this is the same as the bell curve, which we typically hear, but mathematically it is the normal distribution curve or the normal distribution graph. Now this is the bedrock idea against which we make decisions about all the studies, experiments that we do in the social sciences. Now, how does this apply? Let's look at how this applies. So, if we consider this graph here, now, the normal thing that we expect to happen is that most of the scores will fall in here in the middle. Now we put this line here to signify that if you were to be able to fold this graph along this line, in other words, you fold this part onto this part, it will be a mirror reflection. The part here will be exactly the same as the part here. This center line marks the point of the distribution that breaks the scores into two. It is the same score for the median, the same score for the mean, the same score for the mode. So all the three measures of central tendency will fall at this point. The mean will be equal to the median, will be equal to the mode, because of the symmetrical distribution of scores against the frequency that we get when we plot this mathematically. It's a theoretical way of picturing the data that you will get where you're able to sample an infinite number of sample means and then plot their frequency. This is what mathematicians say you should be able to get. Now, focus on this line here at the upper end of the graph and this line here at the lower end of the graph, because this marks the cutoff points for making decisions about the samples that we get when we do a study. Now remember, we said this graph comes out of a theoretical distribution of sample means here on the x-axis that have been plotted against the frequency. So this is the theoretical distribution of sample means. Now, if one were to draw a sample, just a random sample of students who constitute part of the general body of U.S. students. Now, remember, we don't know the actual size of the body of students. But if we were to draw any sample at any time, most of the sample means on this algebra test that is given will fall here in this region. Only a few will fall here at the lowest end. I mean, these people here, their average score is quite low, and we typically don't expect it to be this low. On the other hand, a few will fall at the upper end here. Now, typically, we don't expect many of the scores to fall here. But in the middle here, where it is marked blue, we expect the majority of the scores to fall. Now, remember the experiment that we're trying to do. I am thinking of a way to help students perform well. In other words, I'm going to teach a sample, a strategy that is designed to make them perform very well. And that strategy says that if I, at the end of this study, look at their average score, they are going to be here in this area. Now, of course, that is the only reason why I'm doing this study, because if they were going to be falling at this area, who cares? It's the same for everybody. Most people will score in this region of the graph, so who cares? But you want to do something that will make their performance become very high. That's why you're doing the study. The whole idea for the studies that we do is that we want the sample that we get that goes through whatever study that we have planned to perform in this small, narrow group or samples that score very high, assuming that's what we are looking at. On the other hand, if we are looking for the reduction in something, say, okay, this graph represents the number of cigarettes that people smoke, and we want people to give up smoking, and many people who don't smoke will fall in this, but they are quite few. Quite a majority, maybe nowadays it's not that big here, but maybe in the 50s, when quite a number of people were smoking, very few people didn't smoke. Majority of them would have been in this area. But you get a point. This area will be where I want the people who maybe are smokers but want to give up smoking to be. Now, if at the end they are still here, I've wasted my time. Their time has also been wasted, because they would be just like any ordinary group of people who smoke. So depending on what the researcher is looking for, whether he wants the scores to be at the lower end or at the upper end, this is where you want your scores to be. Now, for the scores to be here at the upper end, you want the probability of getting the scores just by chance to be 0.05 or less. That's why we demarcate this line as the alpha level. That alpha level, the conventional alpha level, is 0.05. point with every experiment that researchers do is to get the scores that they get at the end to be in this region and not in this region. If the scores fall in this region, they mean nothing. Essentially, you've wasted your time. We are going to come to talk about this symbol HO, which is the null hypothesis, and this symbol H1, which is the alternative or research hypothesis. Now, these two hypotheses are mutually exclusive. By mutual exclusivity, what we mean is that if one is true, the other is false. Okay? So if the null hypothesis is true, the alternative hypothesis or research hypothesis is false. If the alternative hypothesis or research hypothesis is true, the null hypothesis is false. That is what we mean by mutual exclusivity between these two hypotheses. Now, before any researcher does his or her research, the null hypothesis says at the end, your scores are going to fall in this blue area, so don't waste your time. The results that you get will not be in this high end of your distribution. Or, on the other hand, if your research is expecting the scores to be at this lower end of the distribution, the null hypothesis says, well, don't do the research because at the end, your scores will not be at this lower end of the distribution. Your scores are going to be here in the blue region, just like any other score that hasn't gone through your research experimental group. So, if you're at the end of your study, your scores fall here, well, the null hypothesis is true because the null hypothesis warned you before you did your study that at the end, your scores will fall here. Don't even waste your time. Now, you carried out your study because you were expecting your results to fall here in this region. Now, the probability of your scores falling in this region is very narrow. It is 5 times out of 100 or less. 5 times out of 100, 4 times out of 100, 3 times out of 100, 2 times out of 100, 1 time out of 100. If the probability is that small, that is 0.05 or less, you can then reject the null hypothesis. That's why we say for this, you can reject the null hypothesis. On the other hand, if your scores do not come any close to 0.05 or less, that is greater than 0.05 or 5 times out of 100. In other words, it's 6 times out of 100, 7 times out of 100, 8 times out of 100, 9 times out of 100, 10, 11, 12, and so on and so forth, then it is not extraordinary. There's nothing unique about it. It is falling in where everyone practically falls. So whatever you did to your people who went through your study was useless. It didn't help them in any way. It is only scores that fall here in this region that you say are unique, because the probability of the scores occurring here by chance alone is 5 times out of 100 or less. That is why we say the alpha level is 0.05. You want your results at the end to fall here and not here, because if it falls here, you have practically wasted your time. So, how does this relate to the studies that we do? Let's look at this. Now, we said the alpha level is 0.05. In other words, the probability of getting your scores just on the basis of pure chance should be no greater than 5 times out of 100. That is what we translate as 0.05. If the probability of a score is 5 times out of 100 or less, then the scores are said to be rare, unique, special, unusual. Speaking mathematically or statistically, we say the scores are statistically significant. In other words, the probability of getting that score just on the basis of pure chance alone is 5 times out of 100 or less. In other words, the scores which are 5 times out of 100 or less are said to be statistically significant. They are rare, unique, special, unusual. And that is what the researcher wants. Because remember, if we go back to the previous graph that we were talking about, this one here, you want your scores to fall here. This is where the probability of getting the scores just on the basis of chance is 5 times out of 100 or less. In other words, if your scores fall here in this region, you're very good. If you are looking at scores that should be low and they fall here in this region, you are good. On this problem of teaching students how to do math problems, college algebra, if my strategy that I've taught them at the end makes them perform here, and the probability is 0.04, I would say the probability of this happening just on the basis of chance is really very, very small. And if it is small, then something must have been the reason why their scores ended up here. And what is it? It must be due to whatever strategy I would have taught them. This is what the researcher wants. You want your scores to be in this region, because if at the end it is in this region, you have practically not done anything at all which is unique. You want it to be unique. You want the scores to fall in this region here. Okay, so to go back, let us go to this idea here. Actually, let's go back to this. Now, if the scores are of the probability of 0.05, 0.04, 0.03, 0.02, 0.01, we say they are all statistically significant. On the other hand, if the scores have the probability of 0.06 or higher, 0.07, 0.08, 0.09, 0.1, all of these scores that are higher than 0.05 are said to be not statistically significant. In other words, they are in that blue region that we talked about earlier. There will be scores that are here in this blue region. We don't want those scores. It's not good. We want the scores to be here. Okay. So, if, let's do this. The null hypothesis before you do your study says that at the end of every struggle, all the problems, all the pain that you've gone through, at the end, your scores will not be in that green region. It will be in the blue region. So it's not going to be different from what people who haven't gone through your study will get anyway. So why waste your time? That is what the null hypothesis says. It says that the probability of your score will be 0.06 or greater. Now, of course, you do not accept what the null hypothesis says. That is why you went ahead and you did your study. Because if you had just listened to what the null hypothesis says and you said, it's true, well, I'm not going to get anything, so then I'm not going to do the study, then you wouldn't have done the study. But you went ahead and did the study anyway because you are challenging what the null hypothesis is predicting. You challenge the null hypothesis with what we call the research or alternative hypothesis. The research or alternative hypothesis states that at the end of the experiment, the probability of getting the scores that you get for your people who went through your study is going to be 0.05 or less. That's why you want to do the study. So, okay, you go ahead and you start the study. And if at the end, indeed, it comes out that the probability of your score is 0.06 or greater, then you have lost the bet to the null hypothesis. So you cannot reject the null hypothesis. On the other hand, if your score for the group that went through your training is 0.05 or less, then you must reject the null hypothesis and accept that the alternative or research hypothesis was correct. And you will be justified in challenging the null hypothesis by going ahead and doing the study. This is the whole idea. So let's look at another aspect, another way of phrasing this. If the probability of the score that you get at the end is 0.06 or greater, and the researcher makes the mistake of rejecting the null hypothesis. Now remember, your probability was 0.06 or greater. In other words, you were in that blue area, but you rejected the blue area and said, oh, your scores were in the green area. You have committed a type 1 error. Now let's quickly go back to that graph and see what the discussion is here. So if we did this, if at the end of your experiment your scores were here, but you said your scores are here, you have committed a type 1 error. You have rejected the null hypothesis that was true. That is what we mean by a type 1 error. On the other hand, if you fail to reject, now I've circled this fail to reject because we don't say accept. Fail to reject essentially means accept. But we don't accept the null hypothesis. It's a term that statisticians use, so we cannot say we accept. If the researcher fails to reject the null hypothesis, in other words, you say the null hypothesis is true, then the researcher has made a correct decision. If the probability of the score is 0.05, that is at the point of the alpha or less, but the researcher fails to reject the null hypothesis, in other words, it is in the green zone, but you say, no, it's in the blue zone, the researcher is committing a type 2 error. It's an error because the results are in the green zone and you must necessarily reject the null hypothesis. If you don't reject the null hypothesis, but you rather reject the alternative hypothesis, you are committing a type 2 error. On the other hand, if the researcher rejects the null hypothesis and accepts the alternative hypothesis, he has made a correct decision. Let us look at, finally, how this thing can be presented in a summary table. So, if we look at this, this is how it should be. The researcher's decision. Here he can reject the null hypothesis, or here he can fail to reject the null hypothesis. If the null hypothesis is true, but the researcher rejects the null hypothesis, he commits a type 1 error. If the alternative hypothesis is true and the researcher rejects the null hypothesis, he makes a correct decision. If the null hypothesis is true, but the researcher fails to reject the null hypothesis, he's made a correct decision. And the last but not the least, if the alternative hypothesis is true and the researcher fails to reject the null hypothesis, he commits a type 2 error.